Okay, can everyone share see my screen?
Yes, sir.
Yeah, okay. All right. So, yeah. Um, okay, so let's do a quick review of what we have learned, and then we will start playing with the data. Okay. So, what we learned over the last almost 7, 8 classes is that there are different types of Fourier analyses that you do depending on the type of signal, and so there are essentially four varieties that we talked about. If you have got a continuous and aperiodic signal that's shown on the extreme left here, then it's Fourier transform. Then you take the Fourier transform, which also gives a continuous signal back. Okay, so it's continuous in the frequency domain, like your original signal is continuous in the time domain, and this is aperiodic. Okay, so that's shown here in extreme left, and in fact, the shown here is a Gaussian, and turns out its Fourier transform happens to be a Gaussian as well, with the standard deviation very small in the time domain, then it's very wide in the frequency domain, vice versa. In the delta function in the time domain, the sigma goes to 0, and then in frequency domain, it will widen enough and keep widening until it becomes a flat. The spectrum becomes flat. So the Fourier transform of a delta function. Let me see if I can draw this here. So if I have a pen, and yeah, able to. So this, 1 second. Let me position this properly. Yeah. So turns out if it's a Gaussian in the frequency domain, and this is the sigma standard deviation, then in the frequency domain it's uh, proportional to 1 by sigma. Okay, so for a very narrow signal like this, the Fourier transform is really wide, and essentially when it becomes a delta function, this will become flat, and makes sense, right? Because if the signal is changing slowly here in time, here, then in frequency, it ought to be more narrow because there are no fast frequency components. It's always changing slowly. So anyway, this is the Fourier transform. Here's the Fourier transform of the continuous signal. If you make the signal periodic, then you take what is called the Fourier series. And the Fourier series is not a continuous function in frequency. So this is the time axis here, and this is the frequency axis here, omega. It's discrete, but there are an infinite number of values that you need. Okay, so it's discrete, but goes to infinity. So it's a countable infinite. Then you can discretize the signal, and now this is a discrete signal which is not periodic. And in this case, you take what is called the discrete time Fourier transform, or DTFT. It is continuous in frequency, but it is periodic. So you only need to worry about what's between 0 and 2 pi. And then finally, if you make a translated and concatenated a periodic signal by translating and concatenating the original signal. So this is now a discrete periodic signal, and its discrete Fourier series happens to be also periodic, but also discrete. So you only need n terms. That's it. And when you take the discrete Fourier transform, essentially that's what you are doing. You are sampling the DTFT at n points between 0 and 2 pi. And it happens to be the same as the discrete Fourier series of a periodic signal obtained by concatenating the original signal, concatenating and translating the original discrete signal. Okay, so this is how they are related to each other. When we compute the FFT in MATLAB, essentially we are doing the DFT. It's just FFT algorithm is just one cycle of the DFT, and its inverse is one cycle of the DFT inverse. Okay, so we had done this, and then we started by looking at the signal. So here's the signal. It's a vector of length 4096, and when I specify what each sample corresponds to in this vector time vals, I get a plot like this. And when I take the Fourier transform, I get something like this, which looks very odd first time when you see this. There's hardly any information. It feels that way at least. And then I just plot the log of the amplitude, because I noticed that the power is very high at very low frequencies and then it falls. And this is what I get for one trial. But I've got 76 such trials. So I actually, when I take the average of those 76, I end up getting a plot like this. Okay, and this is what we had done in the last class. You can see that the power falls off with frequency in every, this is true for all biological signals. And after 500 hertz, it starts falling much faster. And this is because the original signal that I get, I first filter it with a Butterworth filter. I will talk about these filters shortly. And then I sample it. Okay, so this is the action of the Butterworth filter. Okay, and then I had talked about what this frequency axis means. There are 4096 data points, because the n point FFT always gives you n points back. Because they sample your frequency range from 0 to Fs, which is a sampling frequency, I apply this YS here, which tells you what each of those 4096 samples correspond to. So in YS, the first sample, the zeroth sample, the first sample corresponds to frequency of 0, and the 4096th sample would correspond to about 2000. It's not exactly 2000, it's 2000 minus 1 by 4096, also rather 2000 by 4096. Okay, so there are 4096 points. 4096 points which span equally which are equally sampling 0 to 2000. So YS is given by this actually here. In fact, the easier thing to think of this is that YS is just 0 to n minus 1. These are your 0 to 4095. Okay, divided by n multiplied by Fs, which is 2000. So this will basically make sure that these samples are between 0 and Fs minus 1 by n or Fs by n. Okay, is this scaling factor fine, or are there questions here? Do I need to repeat this? Because I'm going to ask a question now, which I asked in the last class also. Okay, so let me ask the question. The question is, when I finally get my signal here, the Fourier transform, the discrete, FFT here, So I've plotted it and I see that there's a nice bump here at 100 hertz that happens to be the refresh rate of the monitor. Typically, you would see bumps at 50, 150 as well, which would be line noise. If you are in the US, it will be in the 60 and 120 refresh rate. Now I want to know that if I look at any two frequencies, so it's a discrete signal here, right? So I'm not, I'm getting some value at here and then here and then here. I want to know what is the spacing in frequency between any 2 points. So that is what I mean by frequency resolution. So what is the frequency resolution here? What does it depend on? Okay, somebody has to guess. I won't proceed until I get an answer. Could be a wrong guess, but at least try. Think about it and let me know. Can you guys hear me? Hello?
Yes, sir. Okay.
Okay. So the question is clear to everyone, right? I'm
The number of points we have, total number of points basically
So how
4096
many points do we have?
samples, and the total
Okay.
frequency range is spanned by.
Okay. So okay. So then what's the frequency resolution?
It is like fs, the frequency, total frequency, sampling frequency 2000 hertz
Yeah.
divided by number of.
Okay. Very good. So now tell me, if I want to improve the frequency resolution, which means that I want these. So what does it mean that I want the frequency resolution to improve? Okay, so this means that I want these points to be closer and closer to each other in frequency. The closer they are in frequency. So suppose there are two oscillations, one at 40 and one at 40, whatever, 2 and, so if suppose there are two oscillations, I'll be able to separate them only if my frequency resolution is very high, which means that these points are very close to each other. If they are not, then I'll end up mixing them because I won't know, I wouldn't know exactly which frequency it corresponds to, right? So having a higher frequency resolution means that these points are closer and closer to each other. So the question is, how do you do that? What does the frequency resolution depend on? So this answer, by the way, is correct. This is the frequency resolution. And it's easy to see from this formula here. Ys is a vector of length 4096. The first point is 0. The spacing between any 2 points is fs by n. And the last point is fs minus fs by n. Okay, so this is the formula. So the spacing is fs by n. And this spacing is the frequency resolution. This is the difference between the first point and the second point and the third point, and so on. So how do I make this number very small? Okay, how do I make this very small? There are only two terms here, fs and n. So
Increasing the data point number.
increasing the number of data points, right? If I make n large, then this number is going to become small. Now the question is, does this frequency resolution, so I'll call this delta f, does this depend on the sampling rate, fs? Now you might be saying that's a very naive question because I do see fs here, but it's a trickier question. And I want everybody here to actually get the trick, find out what's the trick here. At first sight, it seems to be dependent on fs, and it's in the wrong direction. Because if you increase fs, your delta f should become large. No? And as I said, delta f needs to be small to have high frequency resolution. So it seems that if you sample faster and faster, things are getting worse and worse.
But won't capital N depend on fs?
Ah, very good. That's the trick. Very good. So okay, so think about this. N is the total number of data points that I'm taking the FFT over 4096 data points. Right? Now the question is, what's the relationship between the number of data points that I have and the sampling rate? They ought to be proportional to each other, right? If I sample faster, I'll end up getting more data points.
Yes.
Okay. So what's the, so suppose sampling rate is 2000 samples per second, and I have 4096 samples. So what's the factor here? What's the factor here?
Twice logs.
Huh? Okay, let's go back and look at the signal. Got 496 data points, which is n is equal to 4096. And fs, the sampling rate is 2 kilohertz. So I'm saying when you try to relate n with fs, what are you going to multiply fs with? The answer is right here. And you don't need any Fourier analysis for this. Okay, if n is 2000, what does that mean? So sampling at 2000 samples per second, I end up getting samples. And how long would I have sampled the signal for?
See, in 1 second, you will get 2000 samples.
1 second, right? Correct. So 1 second, I'm getting 2000 samples.
So in
So
4000,
if I end up getting 4096 samples, then what is the duration for which I am sampling the signal for?
N by Fs.
It's N by Fs, right? So this term here is just the duration of the signal in seconds. So if I sample the signal for 3 seconds, so T is 3, I'll end up getting 6,000 samples. Right? Because each second I'm getting 2,000 samples. In 3 seconds, I'm going to get 6,000 samples. So the duration of the signal multiplied by gives you the total number of data points that I have. Is this fine? This is okay, right? So now if I apply this logic here, you will see what the frequency resolution depends on. It's actually not dependent on the sampling frequency, because what is N now? N is T multiplied by Fs. The duration of the signal multiplying by the sampling rate. And Fs actually cancels out, you're left with 1 by T. Okay, and this is a very, very important concept to realize, that the only way for you to have good frequency resolution is to actually compute the Fourier transform over a very long signal. So you have to, take FFT over 1 second to get a frequency resolution of 1 hertz. If you take the signal for 1 second and compute its FFT, you will get points that are separated by 1 second, 1 hertz. But if you only take signal which is 0.5 seconds in duration, your delta F is going to be 2 hertz. And it doesn't matter how fast you sample the signal. This is the crucial thing to realize. Okay, so any questions on this? This is actually what we are seeing here is the time frequency uncertainty, which means that in order to determine the frequency content of the signal, you need to stare at the signal for longer and longer durations. Okay, and that's how it is. If you only look at a signal for a very small duration, like 200 milliseconds, then your frequency resolution is going to be as large as 5 hertz. So you won't be able to tell apart a 7 hertz oscillation from an 8 hertz oscillation, because your frequency resolution is 5 hertz. So the longer you stare at the signal and compute its FFT over long durations, the finer is the resolution in the frequency domain. This is the time frequency uncertainty. We'll see it formally later, but this is the sort of like the gist of this. Okay. Is this fine? I'm still not understanding whether you guys are following this or not. So please, but
Yes.
we have to at least agree on this. Otherwise, I can't move forward. In fact, guys are quite silent this year. So, uh, uh, give me something here. Is this fine, or do we need to repeat this?
It's fine, sir.
It's okay, right?
Yeah.
Okay, so good. what is the frequency resolution here? And the answer is 1 by T. And this is independent of the sampling frequency. You can sample a million points if you want. And you will say, hey, if I'm sampling a million points, I ought to have very good frequency resolution because I have sampled so densely. The answer is no. It doesn't matter, because in the frequency domain also, you get a million points here, but you also have to span 0 to million hertz, right? So this thing as this thing scale together with the sampling rate. And actually what matters is the duration over which you are computing the FFT. Okay, and now let's ask another question, which sort of, uh, makes this idea clearer. Now, I am telling you that, okay, my signal has, let's say, 100 Hz component here. And suppose the signal also had a peak at, 40 Hz. Just assume that, okay, or assume that there's another peak at 120 like so. And there are all these other frequencies also. You can see that the power here is quite large. This would be, I think, 0.5 Hertz. This means that the signal has a strong 0.5 Hertz component and a strong 100 Hertz component and so on. So now the question is, where in the signal is this oscillation? Now let me go back. Remember, the signal is this. Okay, and right now I have actually looked at the signal for 2.048 seconds. This is minus 1 point something, 2.8, 0.9 or so. So this adds up to about 2.048 seconds. So my frequency resolution is about 1 by 2.4048, about 0.5 Hertz in this plot. Now my question is, this 100 Hertz oscillation, or this whatever 120 Hertz if there was a peak, or 0.5 Hertz, where is it in the signal? This is not a straightforward question, but everything that we have done so far should allow you to answer this. So think and tell me, where is this signal in? Is it the case that the signal is, present for a short 100 Hertz like this, and then it fades away, or a 0.5 Hertz oscillation like that, and then when the stimulus comes on, it fades away? How can I find out where in this 2-second interval my actual signal is, which is at 100 Hertz or at 0.5 Hertz and so on?
I think it is present throughout, but its contribution to the signal is what is going to be different.
What do you mean by contribution to the signal?
So in the Fourier series, like each of the coefficients associated with a particular frequency, right? So if you've got, let's say, the component, the low frequency component of the signal. So if the low frequency is playing a much larger role than the high frequency, then I mean, the low frequency is there throughout, but it's got a higher coefficient associated with it than the high frequency. So like you will see, like I guess a modulated kind of wave. I don't know if I'm saying it correctly, but
No,
like
yes. Yeah, you're absolutely right, actually. But till the last part. So, so the answer that was given is actually correct. And let me tell you what he meant. Um, so if I go back here and look at the equation. Okay, so right now I'm showing you the DFT coefficients here. So I computed the coefficients here, k going from 0 to n minus 1. Okay. When I try to get my signal from these, I'm just multiplying the coefficient with this. This is a complex sinusoid. Okay, this has a frequency of omega n is e to the power minus j 2 pi by n. So e to the power minus j 2 pi by n. So omega n to the power minus kn is just to the power j 2 pi by n kn. So this thing is just a complex sinusoid, cos 2 pi by n kn plus j sine 2 pi by kn n. Okay, so right now I'm just saying that I'm going to take a sinusoid and multiply it with this, and then take another sinusoid which is k equal to 2 and multiply it by x2, then take another sinusoid which is k equal to 3 and multiply it with x3, and when I add them up together I get my signal back. This is exactly the way we had done the Fourier series also. So what that means is that I'm going to have first a sinusoid which will have one cycle here. And this is your 2 pi by n. Sorry, just 2 pi by n 1 n. Then the next sinusoid that I'm going to have is going to have two cycles, 2 pi by n 2n. And then there will be one DC component. So this will be just the 0th component, 2 pi by n 0n. And then you are multiplying this with x0, multiplying this with x1, multiplying this with x2. These are the coefficients. When you add them up together, you get the signal back. Then you will have x100 sine. There's a sine here, sine and a cosine with that complex formula. 2 pi by n 100 n. Now this term is large. The 100th coefficient corresponding to the frequency is large. But where is that sinusoid here? The answer is that it's everywhere. This coefficient, if I now plot this in a different color, is large, but it's this coefficient multiplied with a sinusoid which is present everywhere. So it's basically a sinusoid at 100 hertz which is present everywhere, and this has a large coefficient as compared to nearby ones because there is noise in the signal which is this coefficient is capturing. However, I don't have any information about where the sinusoid is within this 2-second long signal. I'm assuming that it's present everywhere in this 2-second interval. Okay, and this is the assumption of stationarity. This means that the properties of the signals are not changing over this 2-second interval, which allows me to represent this with a bunch of sinusoids which are of the same length as the signal that I am considering. Obviously, this assumption is violated because, the stimulus comes on at 0 and only stays for 400 milliseconds. Lots of things are changing. But, whenever I take the Fourier transform over some interval, I'm assuming that all the constituent sinusoids that the Fourier transform is going to give me are present throughout the length of the signal. So actually, I have no information about where this 100 hertz component is. Where are these frequency components in the signal? They are everywhere throughout the length of the signal. Very important concept. Please try to understand this properly, because this tells you that the only way for you to actually find out where things are changing in the frequency domain, the only way to do this properly is to consider small durations. Let's say t is equal to 200 milliseconds. Then if you compute the DFT over only 200 milliseconds, you will know that that 200 millisecond interval is where your signal had a particular shape. However, if you try to do that, your frequency resolution will suffer. It will become 5 hertz. So to get better time resolution, you will have to sacrifice your frequency resolution. And in fact, the product of these two is 1. So this is what is called the Rayleigh frequency. It's different from the slightly different from what we are going to define the resolution later on. But the concept remains the same, that in order to improve your frequency resolution, you need to sacrifice your time resolution, which means you have to compute the FFT over very long intervals. But once you get the FFT, you don't know anything about where a particular frequency component is within that entire duration of the signal. So you will say, okay, there's a strong 100 hertz component present in the signal, but it's present over this 2-second interval, and I don't know where it is within that, because I'm assuming that it's present everywhere over that interval. That's the assumption that I'm using when computing the FFT. Okay. So now let me go back and ask the question that when I presented a particular stimulus, remember the stimulus is only between 0 and 400 milliseconds. So I want to know, during this interval, were there any oscillations that were generated? To do that, I need to compute the FFT over a small interval like this. And I typically, there are these sharp ERP components in the first 200 milliseconds. So I actually only compute the FFT over a small interval between 200 to 400 milliseconds. And when so here's the form, here's how we do this. I say that I'm going to compute the FFT over 2 intervals. One is the baseline period before the stimulus came on, and one is the stimulus period after the stimulus on, but between 200 to 400 milliseconds. So this is 0.2 to 0.4 hertz. Now here, this is the formula, which is finding out which time values correspond to these positions. So it's actually just going to find out these positions between minus 0.3 to minus 0.1. And then you are computing the FFT of only those points. And when you plot that, you get this green trace. And likewise, if you replace BL range with ST range, and this will become ST pos, then you will be computing the FFT of just this segment here, 200 to 400 milliseconds. And then now when you compute the FFT, this is what you get. And now you can see something very interesting, that there's a pretty salient peak at about, in this case, about 55 hertz. And there's a suppression at about 5 to 10 hertz. See that? This is the alpha suppression, and this is the gamma enhancement. This means that once I presented the stimulus, power the amplitude of the lower frequencies in the alpha range and a little bit before and after that decreased. So the stimulus, when I presented, generated a gamma wave, which is captured here. Okay, it's pretty cool. We have actually answered the first question that we had asked, which is that whether the stimulus is generating any oscillations, and I have an answer here. Now notice that the spacing between any 2 points, this is 0, this is actually 5 hertz, the next one is 10, 15, 20, right? So now my delta F is 5 hertz. That's because the time duration T is 0.2. If I want to know whether things are changing over 100 milliseconds or not, then I can do 0.2 to 0.3, for example, but then I will get only frequency points every 10 hertz. That's pretty bad. Won't be able to differentiate between alpha and delta and theta and so on, for example. Here also it's pretty bad. As you can see, you don't see any peak at alpha frequencies because your frequency resolution is very poor. The samples are coming quite far. In fact, a lot of signal processing is just to sort of represent the signal properly in both time and frequency domains using a variety of different techniques. But this fundamental limitation remains. You can never overcome this fundamental or limitation, which is the uncertainty in the frequency and the time domain. Okay, this is actually the same concept that Heisenberg, proposed for the momentum of the particle and its position. In fact, the math works out pretty similarly. Gabor and Heisenberg, if I'm not mistaken, actually were able to show this for time frequency also. So it's very fundamental, this uncertainty in determining the frequency components of a signal and where they are present in the signal. This time frequency uncertainty is a fundamental limitation which we are seeing here in action. Okay. So any questions on this? Or is this okay now? Okay, so what I am going to do today for the rest of the class is to actually tell you a few tricks that allow us to understand these concepts a little bit better. So I won't proceed to windowing just yet. So by the way, I'm going to give you guys an assignment next Monday, and I want to make sure that you guys are reading up and following up till this point. So is it okay if the assignment is due within a week? So this sort of forces you to spend some time on this. So I'll give it on Monday and it will be due next next Sunday night. Is that fine? These will be questions that are not very tricky, but it will just force you to go through Oppenheim and Wilsky. That's it. So if you guys don't answer, I'll take it as a yes.
So could you repeat the dates again?
So it will give it next Monday and it will be due next Sunday.
So
I mean,
next
6th.
means 11th, oh sorry, 12th, right?
I haven't
18th.
looked at.
18th?
Yeah. So it will be due in a week. So I will post it on Sunday night, and then next Sunday night you return it back.
So you mean up till this point only? Means
Yeah. Before that's right. So it's just an assignment. You get a week, you read Oppenheimer-Wilski properly, and the questions will be more or less based on the derivations, and it will be just something that you do with a pen and paper. Because now we are starting the MATLAB part, and it seems to me that this some reading and some questions will really help the cause. Okay, so we'll give an assignment this Sunday, and it will be due next Sunday. And please go through this. It will help you going forward also.
We don't have any midsems in this course, right, sir?
No, there are no midsems. So essentially, this will be equivalent of a midsem, I suppose. There will be 4 assignments, each worth 15 marks, and then the grant proposal.
That week right after the submission of this assignment, we have a TFA exam, but I don't know exactly which day it's going to be on because we've not yet decided.
Yeah, so that's that's always going to be the case. Okay, so we'll give an assignment here, but right now I'll tell you a very easy way for us to actually make sense of Fourier transform, and that's actually just based on running some scripts in MATLAB, which are actually really helpful if you are doing this for the first time. Let me just close all these other things. So we'll do simple things. I'll show you a few things, and then we will go from there. So suppose I say my sampling rate fs is 1000 hertz. I am generating here a t vector, a time vector whose length is 1000. So it's going from 0 to 1 second. This 1 second is the duration. Let me just write this as t actually. So okay, we'll do a 2-second long signal. So this t is 2 seconds. So it's got 2000 points. Then I create a sinusoid, sine 2 pi 40 into t. So if I plot y, it's got 2000 data points, and there are 40 into 280 cycles here. So that's a 40 hertz signal. Let me do 10, so it'll probably be easier to see. So plot y. So now there are 20 cycles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 10 more here. Okay, and I could also plot t versus y. So it now shows the signal from 0 to 2 seconds. Okay, it starts at 0 and ends at 0. It's a sinusoid. So now let me just first plot the FFT of y. And you will see that this looks something very weird. Now, why is this so weird looking?
You have not taken the real component, I think.
That's right, because FFT is a complex number. FFT of y, if I just do this, it has 2000 components, but they're all complex. So I ought to plot the absolute value of the FFT of y.
But even then, what is this thing showing? Like, I mean, it's on the real plane, right? So
No, it's actually just shows something weird because if it sees a complex number, MATLAB plots it in the real complex domain. So it makes it weird.
okay.
Okay, so this is the absolute value of the FFT of y now. You can see that there are 2000 data points. Where do you think this peak is going to be? You see that there's a little line here. I guess it makes as, let me do 100 hertz here. So it's now a sinusoid at 100, and I plot the absolute value of y, and I see a peak. Where is the peak? It's actually here right now at 201. Okay. If I had taken a 1 hertz signal, 1 second long signal, so this is a 1 second long signal. Remember now this 0 to 2000 here, 2000 data points are sampling essentially 0 to 1000 hertz. And it doesn't matter whether it's 2 seconds or 10 seconds, it's always going to be sampling between 0 and the sampling frequency, which is 1000. So if I do 1 second and then plot the abs FFT, now you see that the point here is at around 100 hertz, but it's actually shifted by 1 step because the first frequency is not 1 hertz, it's actually 0 hertz. So I need to create another vector which tells you what each frequency corresponds to. And the first frequency that it corresponds to is always 0. And then it's 1 by t spacing. And the final one is fs minus 1 by t. Okay, so this vector now will become 0 to 999. You see there are 1000 points, but the last one is 999. And this is the proper scaling, which will put this sinusoid square at 100 hertz. You see that it's a sinusoid nicely at sitting at 100, and this is the mirror image sitting at 900. Okay, and even if I make this 2 seconds, so I now plot this. So now this is 100 hertz for 2 seconds. Plot FFT. Right now I haven't done the scaling, so it's now showing at 201. But if I apply the scaling here, YS, it will again become 100 hertz. X is 100, right? So that's the frequency here. It's 100 hertz. Okay, and it's a sharp peak.
There a mirror image.
Huh?
Why is there a mirror image here?
Because all real signals are symmetric about the sampling, half the sampling frequency. Okay, so you can think of it as another sinusoid at minus 100 and another one at 100. So this is a real signal, right? So it's cos 2 pi ft plus j sine 2 pi ft. That's a complex number here whose absolute value is what I'm showing. And this one will be cos 2 pi ft minus j sine 2 pi ft, and that will cancel out, giving you the real cos part. That is why your real signals always have another frequency which is minus 100 or equivalently 900. Okay, so I'm looking at the signal between 0 and 2 pi. I might as well have looked at it between minus 1000 and minus 500 and 500, where it would have put this thing at minus 100. It's the same concept that we have seen earlier here, where your Fourier transform of any real signal is symmetric. Okay, so I'm just right now looking at this 100 and 900 like this. But now you can do more cute things here. So for example, let me say that the interval is 2.5 seconds. Or in this case, this is, if it's 2.5 seconds, let's see how this looks like. So I'm going to do CLF. And here, I guess 2.5 seconds doesn't change anything. It's still good. Let me do something else. I'll take this as 1 second, but I will remove this little bit here. Okay, now the signal is slightly longer Then 1 second, it has 1001 points because I'm also including the 1 second. What do you think will happen if I do this? I'm just looking at a slightly longer sinusoid. So the sinusoid doesn't have an even number of cycles. So it's got 1001 points. So the 0th point and the 1001 point are both 0 here. Now when I plot the FFT of y, I'm sorry, the absolute value of the FFT, you will first see that it's got 1001 points, but notice now that it's not a sharp line at 100. It's got all these other things also. Probably easier to see if I just look at the log of this. So you can see now that the power is not only limited to this 100th point, but it has spread out as well. And that's because now the sinusoid doesn't have a complete integer number of cycles. Think about it, even a small change like this, like looking at an interval over which the sinusoid doesn't have an integral number of cycles, can actually change the Fourier transform quite drastically. If I compare this, if I just hold on here and compare this to t minus 1 by fs, it's just one sample that is less. Okay, and compute this and hold on and plot. Look at this. This one with exactly 1000 points on a log scale, this is 10 to the power minus 12. This is like the bit resolution here. So it only has power at 100 hertz and nowhere else. But just adding one extra sample to make it 1001 points actually produces so many other frequencies in the representation. Okay, so we'll continue playing with this for a while. I want to show you a few things so that you guys have a feel for what the Fourier signal looks like. This is a windowing effect that we will lead to. But I really encourage you guys, it's really the time, if you are still coming to terms with this, to sit, open MATLAB, generate random signals. You could just do something like a plot rand of 1 comma 100, which will generate a random number, a random sequence, and compute its FFT, abs FFT, and see what you get. Okay, and in this case, it's a random number, but it has a DC, so it's all power at DC here. If you did rand n, it would have been different. Like this. This is the Fourier transform of a random signal. Or for that matter, just take a signal which is all zeros, 1 comma 1000. So this is all zeros, and just make x the first coefficient as 1. So now this is like a delta function, 0 everywhere except at 1. And then find out what's the abs FFT of x. And this, as you can see, is a flat line. This is the Fourier transform of a delta function, which is power at all frequencies. These little things playing around with MATLAB will go a long way in for you to understand how the Fourier transform works. Okay, it's a really useful exercise. We will continue with that in the next class. Sorry, I've run over time now, so I will stop now.